In this video, we're going to look at a rather interesting example of using the fundamental theorem of calculus to help us answer questions about a derivative. So the situation for our question is what I have in this box over here at the top. Okay, so what we're dealing with is we have the graph of y equals some integral from 0 to x of L of t dt, where L is a piecewise constant function. Okay, that's going to be kind of important to us. And then it's graphed here and shown below. So let's talk about this L being a piecewise constant function bit. Okay, by the fundamental theorem of calculus part 1, and this is kind of the big main idea of this video, is that whenever we take the derivative of this y here, the way that it's defined by using the FTOC part 1, we get that the derivative of y is equal to L of x, right? So what that tells us is that our y prime is defined as a piecewise constant function. Okay, so then going kind of backwards for a second and thinking, okay, y prime is this is y. Whenever we take the integral of this L, this piecewise constant function, the integral of any constant, according to the power rule of integration, is going to give us a linear function back, right? So say we take the integral of 3 with respect to x, we're going to get 3x back. Okay, so that's kind of how the shape of this graph comes from. Because we're taking the integral of a piecewise constant function, we're going to be graphing a piecewise linear function. Okay, so that's kind of the gist of what we have going on here. And for right now, what we're going to do is we're going to kind of ignore the shading, because by the way that this problem is set up, L being a piecewise constant function, what that tells us is that our function y that we're really concerned with is just this boundary line. The reason why it's shaded is because we've defined it to be an integral, but by the nature of the problem and the specifics of what we're dealing with, the only real things that we're going to be concerned about with this y prime and with this y is just the boundary line. So the shading is almost kind of irrelevant in this question. We're going to get further into that with part 3, finding the average value. Okay, but for part 1, what we're going to be dealing with is asking ourselves, where is L positive, where is L negative, and where is L equal to 0? Okay, well, we said that y prime equals L of x. So these questions about L being positive are questions to us asking about the derivative of y, or namely, the slopes of y, right? Because we talked about how the derivative is the instantaneous rate of change of a function. So y prime is talking about the slopes of y, or the slopes of the boundary line that we have graphed here. Okay? So what we're going to be dealing with now is just looking at where is the slope of y positive, because that's going to tell us the information of where L is positive, where L is negative, and where L is equal to 0. For L to be positive, the slope has to be positive of our graph. For L to be negative, the slope has to be negative, so we kind of have a good idea of where our intervals are there. Then this L equal to 0 is kind of interesting. We'll get to that here in a second. Let's go ahead and put down our answers for where L is positive. Okay, so on this interval here, we're looking at the horizontal axis here. We're going from the value of 0 to 2, right? We have a positive slope here. So know that interval gives us a positive slope. So that means that L is positive in this case. And then again, we see another positive slope ranging from 5 to 9, right? So that's another positive slope that we have. So those are our two intervals where L is positive. And then the other two intervals here, we go from 2 to 5. We kind of fill in the blanks there. And this shouldn't be negative 2. This should be positive 2. That was my fault. By filling in this gap here of 2 to 5, looking at our graph, we know that our slope there is negative, so that means that L is negative. And then, finishing off the graph, because we've graphed from 0 to 12, we know that the interval of 9 to 12 is also negative. So at those points in question, where we have these kind of breaks of our interval, right, where we're looking where we suppose to be a max or a min in here, for our derivative to be equal to 0, our derivative first has to exist. That's kind of this underlying technicality that we sometimes skip when dealing with smooth curves. And the key word there is smooth. We're not dealing with a smooth transition of the change of the slope going from here to here, right? It's rather abrupt. It goes from this slope, which we'll find later, then goes to this slope rather quickly. It snaps off. There's no kind of smooth curve about it. So when we don't have that smooth curve, at this point here, this 2, this 5, and this 9, where we suggest there could be a max or a min, or we could have a derivative equal to 0, we actually don't have a differentiable derivative at that point at all. So our derivative can't really equal anything. And I don't mean can't equal anything as in equaling 0. It physically, like, it doesn't exist there. So whenever we have wherever we have this kind of this derivative where it doesn't obtain a value because it's not differentiable there. What we're going to get as our response for this part is that we have no spots in our graph where the derivative is actually equal to 0. Okay, we have some undefined spots where like the derivative doesn't exist at all, but that doesn't tell us that the derivative is equal to 0. Okay, so we've answered all of part 1. We found where it's positive, negative, and equal to 0. Well, now let's look at L sub max and L sub min, or namely where the maximum and minimum values of L exist. So keep in mind again, we're dealing with L, which is the derivative of what we have here, graph, right, this boundary line. So what we're dealing with for maximum and minimum values of L are going to be the steepest slopes that we have in the positive direction for our L sub max, and the steepest slopes we have in the negative direction for our L sub min. Does that make sense? We're dealing with the maximum, or like the highest value that L achieves, so that's the steepest slope in the positive direction, and we're dealing with the minimum value that L achieves, which is the steepest slope of Y in the negative direction. Okay, so in order to answer that question, let's figure out our slopes on these intervals. Okay, and I'm going to kind of use what we have up here and denote what our slopes are up here. So I'm not going to write equals, we'll just put different colons on there just so that we have information tied to those things. Okay, so going from 0 to 2 here. We go from -4 and we rise 2, so the rise component of our slope is 2, but then our run component is also 2. We go 2 over 2, right? So 2 over 2 gives us a slope of 1. So on this interval, we have a slope of 1. Okay, positive, good. Let's look at the slope going from 2 to 5. Well, here we fall 6, so that means that we're rising in the negative direction, 6, and then we run 3, right? So this gives us a slope of -2, okay? And then using rise over run again, here we rise 8 and we run 4, okay? So we get a rise of 8 and a run of 4, so that gives us 2. So out of these two right here, because these are the only places where our slope is positive, the steepest one is 2. So our L sub max is the steepest slope of Y that we have graphed here. I don't know why that's not drawing right there. Let me fix that. So our steepest slope in the positive direction for this graph is 2, okay? And then we need to see if this other slope that we have here is going to be steeper than -2 for it to be our L sub min. Well, here what we're going to do is we're going to fall 9, going from 0 to -9, and run 3. So here we go, -9 over 3, which gives us -3. And sure enough, that's a steeper slope than -2. So our L sub min is -3. So what we did there was, again, we thought about how to think about these questions in terms of the derivative of what we had graphed, or namely looking at the slopes of the piecewise linear function that we had going on there. Okay, and I kind of want to take that as an extension here and actually graph this L of x function. So the intervals that we have, that we gave in part 1, are going to be what we plot on this x-axis here, right? So we go all the way out to 12, so that's 5, 6, 7, 8, 9, 10, 11, 12. We're going to go all the way out here, and like I said, this axis that we have here is going to span, I got a little ahead of myself, it's going to span from -3 to +2. So we get this going on, right? So what we're going to graph is the x-axis is going to be the intervals that we have here, and then the y-axis is going to be the slope of the L of x, or the L function that we have graphed here. Okay, so we said from 0 to 2, excluding the endpoints, because we talked about how it's not a smooth curve transition, so the derivative doesn't exist, and that's what we're graphing, is the derivative of L, right? So what we talked about is from 0 to 2, we have a slope of 1, right? So we have an open hole at 1, or at 0, and an open hole at 2, graph this constant of 1, right? And then our next interval, 2 to 5, we're going to have a plotting of -2, right? So we go from 2, 3, 4, 5 right here, and this is at -2, okay? So then the next interval we have is 5 to 9, and this is graphed as +2, so 6, 7, 8, 9, right there. So from 5 to 9, we have a value of 2 on our graph of L of x. And then, lastly, the last interval, 9 to 12, has a value of -3. So this is the piecewise constant function, or L, that we've been dealing with so far in this question, right? So what we've been dealing with so far is, now that we can see what we have with L, the values of 0 to 2 and 5 to 9, those intervals are positive on L, right? Like, we're actually looking at L. So these are the positive intervals of L, and these are the positive intervals of, or the negative intervals rather, of L. And then we also see kind of how we got to this conclusion of no values of L being equal to 0. We have that, right? Like there's no point where L touches the x-axis. So we're all good there, and we've kind of reaffirmed what we thought, that we have an L sub max up here of 2 and an L sub min of -3, right? The maximum and minimum values of L. So it's just a cool kind of connection or extension of what we've been dealing with so far. But in this question, we have one more part to deal with, and that's dealing with the average value of our L function over 0 to 12. Okay, so what we're going to do is we're going to use the average value function that we learned a couple sections ago, right? And namely what that is we're going to have 1 over b minus a, our interval, right, 0 to 12. So that's going to give us 12 minus 0, or 12. And then we take the integral from 0 to 12 of this L of t dt function. Okay? But then what does all this mean? What does the integral of 0 to 12 of L of t dt actually look like? And that's what we're going to try to explain and kind of look at right now. Whenever we look at the integral from 0 to 12 of L over t dt, the way that we come to this original definition, or where we kind of came from, is that this 12 takes the place of this x, right? That's kind of what we've put in there. We've taken y of 12 to be the integral from 0 to 12 of L of t dt. That's kind of where we're at right now. So what we need to kind of think about is, let's think of another example of this information on this graph that we can use to kind of help explain what we're getting ready to do. So let's ask ourselves what happens when x equals, say, 5. Okay, let's let x equal 5, and we'll come do this work down in here. So whenever we're taking the value of y of x, I'm just going to rewrite what we have up there so we can scroll down and have a little bit more room. Whenever we let x equal 5, what we're getting is a translation of what we have here. Or not, a translation, like actually not sliding or a transformation of something, but translating it from being in x terms to 5. That's kind of what I mean there. So what we have is this going on. But then whenever we were talking about the graph of y, right, earlier, we said how y is just the boundary line of what we're graphing, right? So that means that y of 5 is going to equal -8. It's going to actually equal the y value that we get whenever we plug in x or we plug in 5 for x, and it's going to return the value that's on the boundary line. So what that tells us here is that this integral 0 to 5 of L of t dt, using this dummy variable of t with respect to t and all that we're really evaluating is the function's value at 5. Okay, does that make sense? Because we talked about how y is simply just the boundary line that we've been dealing with so far. So we're dealing with just the function's value, not necessarily worrying about evaluating the integral from 0 to 5 of a function that we don't really know how it's defined other than it being piecewise linear. Okay, so what we're going to end up getting here for this case is that this integral from 0 to 12 of L of t dt, we can translate that, right? We can translate that to y of 12, just like we saw y of 5 being the same kind of thing here. But then, when we evaluate x as 12 on our y, what we're going to get for our y value in return that this evaluates to is -9. So here we're going to get 1/12 times -9, or -9 over 12, which simplifies to -3 over 4. It's going to be our answer there. So whenever we're dealing with the average value of something like this, it's not necessarily going to be an evaluation of the integral that we're looking at. What we have to do instead is think of what's graphed, how do we translate that, how did we get there, how can we make that make sense for us in our own way so that we can get to something like this, solve it and simplify it to give our average value. Okay, so this application of the fundamental theorem of calculus was a little bit more conceptual. It took a lot of thinking for us to kind of think about what we were doing, where we were going, and kind of where we ended up. When we were dealing with L being positive, negative, that's dealing with the slopes of what was originally graphed of our boundary line. right? So what we were dealing with there was just the slopes of our boundary line. Wherever it was positive, L was positive. Wherever it was negative, L was negative. We went over a quick little review of the derivative existing at certain spots and how that kind of disqualifies it from being equal to 0 or equal to anything in that, right? We looked at the maximum minimum slopes or maximum minimum values of L, and really all we kind of did was just had a big conceptual problem to look at, okay? So like I said earlier, the shading is kind of there to not necessarily confuse you, but it's there to make you think. It's there to make you think of like, okay, what am I actually doing? How can I use the fundamental theorem of calculus to help me solve this problem? How can I use it to help me make sense of what I'm looking at? And that's what we looked at in this problem.